This paper presents a new approach for style-aware facial animation. Starting from multi-view video, we represent the captured facial performance with a combination of blend shape geometry and dynamic textures. In order to allow for animation and editing of facial expressions, we generate a parametric face model, based on a variational autoencoder that learns a joined latent space for facial expressions. Both face geometry and texture are reconstructed from the same latent code that accounts for shape as well as appearance. For better control and more flexibility, we generate two separate expression models. One for the mouth and one for the eyes. While the hybrid model provides an efficient and accurate representation of facial expressions, it is not sufficient to generate photorealistic renderings. Especially the silhouette, ears, and the appearance of hair cannot be reconstructed well, but also glasses pose a problem as they cannot be captured by the underlying blend shape model. Therefore, we employ a neural rendering method, which uses a convex combination of the mesh-based rendering, a corrective image and the static background as image formation model. The neural network predicts a corrective image alongside with 3 weight maps that represent the influence of each source image. This allows for synthesizing realistic videos of the animated character. In addition, the predicted weight masks provide a foreground segmentation of the final rendering result, which simplifies the integration into new backgrounds. In the following videos we show more and longer rendering results. All results are based on an evaluation sequence that was not used for training. In order to evaluate our approach, we trained 3 recent methods for face modeling and rendering on a publicly available dataset. The following videos contain rendering results of all methods including the ground truth. All results are based on an evaluation sequence that was not used for training. This video shows a close-up comparison between our work and the approach of Gaffney et al. It can be seen that our model is able to reconstruct more details for the skin, hair, and even fine reflections on the glasses. As their approach provides foreground segmentation as well, we also compare the resulting alpha masks. Again, our method synthesizes more accurate and cleaner results. In order to synthesize facial animations from speech or text, we capture several training sequences of an actor with different emotions and speaking styles. While the spoken content is automatically annotated and converted to Vism sequences using forced alignment, we do not create labels for emotions or speaking styles as we want to automatically learn a latent space of animation styles during training. This video illustrates the variety of captured training sequences. They include powerful facial expressions, strong head movement as well as different emotions. In order to deal with this challenging training data, we employ a sequence-to-sequence translation approach based on a convolutional architecture. The animation network converts a sequence of Vism IDs into an equally long sequence of animation parameters. This holistic approach allows for modeling global effects such as style or movements, which are not directly related to the content. In order to represent different emotions or speaking styles, we introduce a style encoder network. During training, the style encoder receives the target animation parameters and extracts a single latent style vector that enables the animation network to synthesize different emotions or speaking styles. During inference, the style vector can be used to control or modify the animation according to the user's needs. The following videos show different animations synthesized from the same input sequence but with different style parameters.
Those musicians harmonize marvelously.
I tell you a story about a girl. This girl is 5 years old. She lives in a big flat in Berlin.
Since eye expressions and head movements are not well correlated with the spoken content, we introduce animation priors for eyes and head pose. These priors reduce the solution space and ensure that only realistic animation parameters for the eyes and head pose are synthesized. The following videos illustrate the impact of the proposed priors on the animation results.
And paying great attention to the press work or actual process of printing, so far as fine printing is concerned, though paper did not get to its worst till about 1840.
While the dominant effect of the priors is the reduction of noisy head movement, they also affect the eyes by minimizing unnatural eye expressions. In order to evaluate our animation method, we trained 3 recent methods for facial animation on our captured dataset. The following videos contain rendering results of all methods. All results are based on an evaluation sequence that was not used for training.
I tell you a story about a girl. She lives in a big flat in Berlin. This girl is 5 years old.
For all experiments, we trained our animation network on sequences between 2 and 10 seconds. However, this does not necessarily limit the maximum duration of synthesized animations, as the proposed convolutional architecture is able to generate even longer animation sequences. This is demonstrated by the current video, which has an approximate duration of 25 seconds.